Uh, Hello, am I audible and visible? Okay, we'll wait for 5 more minutes and we'll see whether anyone joins or not. After that, I'll start with the session. Okay. Hi, we'll wait for 2 more minutes to see whether someone joins or not, and after that we'll start. Okay. So am I properly visible and audible?
Yes, ma'am.
Okay. So it's already 7:05. I'll start with today's session. Let me introduce about this first. You are already undergoing the course of heat transfer in NPTEL of Professor Sunando Dasgupta. And this is an add-on that has been started by NPTEL that will be just a problem solving session. Like every week, we will undergo these sessions, and whatever you will be learning in class, we will do various problems based on that topic, so that it will brush up your skills. It will help to improve your problem solving and will help you in future preparations, like for your BTech or any other exams if you want to crack gate. So yeah, myself Kalpita Nath, and I am research scholar of IIT Kharagpur itself. Okay, second. So I hope you will enjoy the session. So this is the first class of this problem solving session, and without further ado, let us start the course. So I'll go towards the first question. Is the question visible to all? Is the question visible?
Yes, ma'am, it's edible.
Okay then. So we have already learnt in the class about conduction, heat conduction. So if there is any solid body, and if the temperature on both the surface is different, and any thermal conductivity is like every surface will have a specific thermal conductivity. So there will be transfer of heat from the hotter surface to the colder surface. That is the basic phenomena that is happening. So with the first question, we'll understand how to apply that theory. So, what is there? There is a surface where on one surface, like in this slab, on one surface the temperature is 40 degrees Celsius, and on another surface the temperature is 20 degrees Celsius. It's clearly like indicated in the diagram itself. So we can see that the heat flux is given as 40 watt per meter square, right? And the thickness of this slab is 0.05 meter. So this question is pretty simple, like how to like calculate the thermal conductivity of the wooden slab. So I'll give you 2 minutes to solve this, and just one basic equation will be applied that sir have already taught you in the class. I'll help you solve this, but first try out with yourself. Okay, anyone have any doubt regarding this question? You may unmute and ask. Okay, then I'll give you 2 minutes, and just apply the. Okay, then just apply the equation. I won't name the equation right now. Just apply the equation which is feasible in this case for heat conduction. The basic equation that is applied for heat conduction, and then give me the result. Like what will be the thermal conductivity of the slab? Okay, let's start.
Ma'am, is the answer option B?
Okay, let me check. Yes, option B. Anyone else? Yes, option B only. Just tell me which law is applied here.
Ma'am, Fourier's law of heat conduction.
Okay, sure. So we'll proceed towards the solution now. So let me share another slide. The slide is visible, right? Okay, hello. So yeah, in this
Yes,
way
ma'am, it's
only, just
visible.
applying Fourier's law, we can see here, we know that by Fourier's law, Q is equal to minus K upon like into delta T upon the distance, like where the transfer of temperature will take place. So just we'll use this equation. Temperature is given as the one side temperature is 40 degree, another side temperature is 20. So we'll just we have just applied the temperature difference and just have applied the thickness of the slab. The thickness of the slab is given as 0.05 meter, and the heat flux is given as 40 watt per meter square. So by that we can clearly see that the thermal conductivity came out to be 0.10 watt per meter Kelvin. So yeah, the answer is option number B. Okay. Let's proceed to question number 2. So these are pretty simple question, right? So let's proceed to question number 2. Okay. Okay. So what is question number 2? Thermal diffusivity of a substance is what? It is inversely proportional to thermal conductivity, or directly proportional to thermal conductivity, or directly proportional to the square of thermal conductivity, or inversely proportional to the square of thermal conductivity. Anyone who want to answer? Just remember the formula of what the thermal diffusivity is. So how thermal diffusivity is related to thermal conductivity? Unmute yourself and answer the question.
And it's option B.
Okay. Correct. Anyone else? Okay. So let us check this. So yeah, thermal conductivity, like thermal diffusivity, what is that? It is heat conducted upon heat stored. That is K delta T upon rho Cp delta T. So obviously thermal diffusivity is directly proportional to thermal conductivity. That is option B. Okay, so let us now share the question slide again. Okay. So what is the third question? The equation that describes the one-dimensional unsteady state heat conduction with no heat generation for plane wall of thickness L with W and height H is which one of the following? Remember there was one derivation that sir taught on class where, yeah, let's check the answer then. Answer is option number C. See, the most common form of heat diffusion equation, sir have already taught on class, with one derivation where heat inflow and outflow was calculated and how much heat generation took place and how much heat stored. So by that, and heat transient was there. So from that we came to this final equation where K is the thermal conductivity, del square T del x square, temperature was distributed in three spatile direction, that is x, y and z. So Q dot is the heat generation and rho Cp dt del T del T. Okay, so T is small t is here the time. There is the variation, the temporal variation of temperature. Okay, so let us now what is said, it is one dimensional flow. So obviously y and z won't be there, only x will be there, and heat generation is also not there, right? What's said? Heat generation is also not there. So okay, so the option will be C. Okay. Now let us proceed to next question. A composite wall of a furnace has two layers of equal thickness delta, having thermal conductivity K in the ratio of 3:2, which is the ratio of temperature drop across the two layers. Same equation will be applied, the Fourier's law. Solve this and tell me the answer. I won't be able to see the meet. So if anyone wants to answer, kindly unmute yourself and answer.
Ma'am, is the answer option A?
Let's check. Yeah, option A. Someone is there. Okay, so this is the question which we are working on now. Someone has already answered, and whoever have joined now, kindly look into the question and then we'll discuss the answer. Okay, so I'll discuss the answer now. Or anyone else is there who's solving? If anyone is solving, you may interrupt me or I'll move towards the solution. Okay, so I'll move towards the solution now. Okay, so here the thickness is given as same. So the thickness here is indicated as delta. So delta 1 is equal to delta 2, and K1 upon K2's ratio, that is thermal conductivity ratio, is given as 3 upon 2. So if the heat, that is what is said in the question, the heat that is transferred is same. That is uh, uh, like if there is a composite wall, if heat will flow from one direction, then the same heat will move out, right? As there is no heat generation or no heat add up. So as the heat will be same, that is entering and that is leaving the both of the surface. So heat we can equalize, and by the Fourier's law, we know that Q is equal to K1A delta T upon the thickness. So we have just equalized both of them, and from that area, as it is composite wall, so area, just one second. Uh, so as it is composite wall, so area, the surface area will be same for both of the walls, and the temperature difference we have to find out. So if delta 1 and the ratio of the thermal conductivities are given, excuse me. So from there we can find out that delta 1 and delta 2 are also similar, so they also cancels out. So delta T1 upon delta T2 is equal to K2 upon K1, that is equal to 2 by 3. Understood? Anyone have any doubt? Or should I
No,
proceed further? Okay. So I'll proceed to the next question now. Okay. So here, as we can see, there is a temperature distribution been given of an this is suppose a medium of an infinite body, and the temperature distribution is given over there at a given instant of time. So assume the constant properties of infinite medium and no internal heat generation. Choose the correct option. At the given instant of time, the temperature is linearly dependent on time. Second one, at the given instant of time, temperature is independent of time. And at the given instant of time, temperature is dependent on X only, or none of the above. So I'll give you 2 minutes for this. If anyone is wanting to answer, you can unmute and answer me. If you are having any doubt regarding the question, kindly unmute yourself and then ask me. Let me share the question separately so that I can see if anyone is replying in the chat box. Whoever have joined now, this is the question that is being shared now. So there is an infinite body, and at a given instant of time, the temperature distribution is being shared, and we have to assume the constant properties of the infinite medium, and no internal heat generation is there. So choose which of the following options is true. So at a given instant of time, temperature is linearly dependent on time, or at a given instant of time, temperature is independent of time, or at the given instant of time, temperature is dependent on x only, or none of the above. Anyone is having doubt regarding solving this? You want any help?
Can please explain the answer?
You are able to solve, or you are having any doubt?
Ma'am, I think the answer is option C.
Option?
C.
No, 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 it's not option C. Sanchita, let us wait for 1 or 2 more minutes if anyone solves or not.
Yes, ma'am.
Yeah. Okay, so someone have answered. Okay. I'll wait for 1 more minute, whether anyone answers or not, and then we'll proceed with the solution itself. Okay, so let us proceed to the solution now. From later this week, from the next week itself, we'll solve the questions on a writing pad. Okay, for this week only, the answer is represented in a presentation slide. Okay, I hope it's visible. Okay, so we can see that we already know about the heat equation for the conduction. So we have written it as del square T del x square plus del square T del y square and del square T del z square plus Q dot is there, but as Q dot, that is heat generation, is not present here, no internal heat generation is there, that's why we can cancel it out. And rho K upon rho Cp, that we have represented as thermal diffusivity. Okay, so 1 upon alpha del T del T. Now T is a function of x, y and z. Okay, so if T, x, y, z satisfy this relation, the conservation of energy is satisfied at every point in the medium. That is, the equation of temperature that is given, it should be satisfying the heat equation that we already know, because this heat equation is derived by the conservation of temperature, like conservation of heat. Okay, so we can substitute this the equation of T, that is here in the main heat equation. We can substitute the temperature equation that is already given in the question. That is, in the question it's given as x square minus 2y square plus z square minus xy plus 2yz, right? So we'll just substitute this here, and when we will substitute this, we'll find that this will form this following equation, that is del t del x will be 2x minus y, del t del y will be minus 4y minus x plus 2z, and del t del z is 2z plus 2y. So if we will solve this, we find that del t becomes 0. What does that imply? That implies that the prescribed instant, that is at the instant, the equation that is applied for this system is independent of time. So someone have already answered this in the chat box. So yeah, the option is answer B. So Raza have answered the correct option. Okay, so let us proceed to question number 6 now. After the next question, we'll take a break of 2 minutes if you guys want, otherwise we can continue. Okay. Let us proceed to question number 6. So question number 6 and 7 are a linked question. So in this question, the temperature distribution in a one-dimensional wall with thickness and thermal conductivity is given. So thickness is given as 50 mm and thermal conductivity is given as 50 watt per meter Kelvin. Right? The question is visible. Yeah. Okay. So the temperature equation is also given. Temperature distribution, it is given as A plus Bx square. It is given as A plus Bx square. Just 1 second. Okay. Where A is given as 200 degrees Celsius and B is given as minus 2000 degrees Celsius per meter square. So we will assume a steady one-dimensional flow with constant properties, and so what will be the question number 6? for question number 6, we have been asked what is the heat generation rate in the wall, that is Q dot. So we already know that which equation we need to apply. Okay, so solve this. I am giving you 2 minutes for this and then we'll proceed with the solution. Anyone having any doubt with the question? I'll open the linked slide. Yeah. And for the first question, you have to find out the heat generation Q dot. Anyone? Anyone is up with the solution? Okay. Let me check. No, the answer is not correct. No problem, you try. I'm waiting for a few more minutes. Like, sorry, was I muted? Okay, okay. The answer is not correct. Sharif. So, no problem. I'll be waiting for 2 more minutes for you to correct this. Till now, how you have solved whatever equation you have applied, just the same equation will be applied here. Just start from the basics. Okay. So one have said option D and another have said option A. Anyone else want to answer? Okay. Okay. So I'll proceed with the solution now because we have given. We have given too much time on this question. So I'll share the solution slide. Okay. So we already know the heat. Second. Don't know why people are joining this late. Okay, fine. Uh, okay, so the appropriate form of heat equation for one-dimensional steady-state flow. Okay, so first heat equation we have already seen. Just let me show you. This is the total heat equation, right? So here it is one-dimensional flow. So y and z will be cancelled out, and it is steady state. Steady state. So t won't be there. That is the temporal variation won't be there. So heat generation will be there, and we have to find out that q dot is equal to minus k ddx of tt dx, right? So now T is already given in the question. What it's given? It's given as a plus bx square, right? So we'll just put it there. So it will be 2bx, and so what will happen now? Ddx of 2bx, it will be only 2b, so minus 2bk, and b is already given as minus 2000 degrees Celsius per meter square. So the heat generation will be 2.0 into 10 to the power 5 watt per meter square. Sorry, meter cube. This is the heat generation per unit volume that is asked to find out in this question. Okay. So what will be the option? This is, just one second. This is option number A. Yes. So someone have already answered this in the chat box. So yeah, you're correct. The option will be option number A. Right. Okay. Now let us share next question. Okay. As this is the link question, in the same question, what is it asked? It asked us to find out the heat flux at x is equal to L. That is, at x is equal to L, that is at 50 mm, at this surface, we have to find out the heat flux. That is, we have to find out Qx double dash L. Right? How to find out? Okay. So I'll give you some time to solve this. Try out this question. I'll share the question part. This is the question. Option C. Let me check. Okay. Let's wait for 2 more minutes. Let's other answer. Then we'll proceed to the solution and I'll tell you what the correct answer will be. Okay. Okay, many have answered the question. I'll proceed to the solution then for this question. Okay. Okay. So the heat fluxes for the phases can be evaluated from Fourier's law. Okay. So by Fourier's law, we already know that minus k qx at x will be is equal to minus k dt dx. So using the temperature distribution Tx to evaluate the gradient. So Tx is already given, that is a plus bx square. And if we will solve this, then the heat flux comes out to be minus 2k bx. The fluxes at x is equal to 0 and x is equal to L are then at 0, it will be 0. If we will put 0 at x's place, and if we will put L at x's place, it will be minus 2 kBl. And all the values are given, that is thermal heat conductivity is given as 50 watt per meter Kelvin, and B is also given as B's value. It is a constant and its value is given as minus 2000 degrees Celsius per meter square. And also the value of L is given as 0.050 meter. Okay, so the flux at L comes out to be 10,000 watt per meter square. That is option number C. So yes, you all are correct. Let's proceed to the next question. Watt per meter Kelvin is the SI unit of which of the following? This is relatively simple question. Yeah, Chinnappan, tell me. You have raised your hand. Yeah, correct. Okay. So then the next question is the convective heat transfer coefficient does not depend on which of the following. So I guess we have already studied the basics of convection. So do we know about what the convection phenomena is? Can anyone tell me? Anyone? No? Sir haven't taught this in the class? The basics, you remember. It's in third or fourth lecture, I guess. Sir has just given the basics of it while he was deriving um, uh, the thermal, the heat conduction equation. At that time, he have said about the basic of convection? Like which equation has been applied there? Anyone? What is convection? Do you know how many modes of heat transfers are there?
Yes, ma'am.
How many? Yeah.
Three.
Now, which are there? Tell me the names.
Conduction, convection, and radiation.
Okay. So, in that only convection comes, right? So, what is convection? I just want to know the basic of it. What do you know about convection? Just any example that comes or crosses your mind.
Ma'am, forced convection and natural convection.
That is, yeah. So, that is a later topic. So, what is the forced and natural convection? An example that can distinguish between them? Yeah. Hello.
Ma'am, suppose, ma'am, in a free convection, suppose the hot plate is kept in a room, then and and the heat transfer takes place automatically. There is no external agent used.
Hmm. And what is forced?
Mm, ma'am, if an external agent is used, for example, blowing fan or something, then heat transfer takes place.
So, what is
Valid.
the equation that governs the convection?
Ma'am, Newton's law of cooling.
Okay, so then what will be the answer here?
Ma'am, option A.
Correct. Okay, so good. And many have, I can see already answered this. Yeah, correct, Sharif. So, A is correct, option A, and not C. Okay. Hmm. Why? Because the Newton's law of cooling is that governs the convection, right? So Newton's law of cooling is dependent on temperature difference, not the temperature gradient. That is, gradient means in a specific space, if the temperature is changing, like in a solid surface, temperature is changing, right? So as convection doesn't take place on a solid medium, it takes place on a fluid medium, right? So there the distance doesn't matter, so the gradient doesn't matter, only the temperature difference matters. So let us check this answer, so we may have a better understanding of this, right? So here we can see that it is a fluid on the left side and solid on the right side, right? So from the fluid is heated up at infinite surface, like all of the fluid, as convection is taking place in the fluid, so the temperature is same everywhere. So we can say that the at infinite place of the fluid, that like that at any point in the fluid the temperature will be T infinite, and at the interface of the fluid and solid the temperature is Ts. So if we take the temperature difference, that is T infinity minus Ts, it's written wrong because here temperature is the infinite is greater as compared to S, the surface. So T infinity minus Ts into H into A, this is the heat flux. Okay, so so the answer will option A. Now let us proceed to the next question. We have few more questions left. What is the mode of heat transfer in solid? This you all know already. Yeah.
Conduction, ma'am.
Yeah. Correct. Correct. Now let us proceed to the next question. Okay. So this is yet another problem. Mm, what is this? The thermal conductivity of an insulating material is measured. So we have to find out the thermal conductivity here. The temperature of the flat slab of 25 mm of material is measured to be 318.4 Kelvin at one surface and 303.2 Kelvin on the other surface. The heat flux is measured to be 35.1 watt per meter square. So what we have to calculate? We have to calculate the thermal conductivity of the material. Okay. These are the options that are given, and the picture clearly identifies what the problem is. So we have to find out the thermal conductivity. Simple question, right? So solve this and answer me.
Ma'am, option B.
I'll tell you whether it is correct or not. Just let us wait for a few more answers. Anyone else? Okay. Okay. Anyone else? Okay, let us see. Anyone else who wants to answer, or should I proceed? I'll try to keep more questions in the next week, upcoming week, because we have to undergo a class of 2 hours, right? As you are really fast with the solutions. So I'll keep more questions from the next week. It will improve your problem solving. Okay, so let us proceed to the solution now. Okay, so first what we'll do, we'll use Fourier's law for heat conduction again. So by that it is Q upon A is equal to minus K dt dx is equal to K del T upon del x. So heat flux is given, that is Q upon area, that is the heat flowing per unit area is given. So heat flowing per unit area, that is 35.1 watt per meter square. It's already given in the question. And temperature is given as temperature difference is given as 318.4, that is on one side, and another side is 303.2. So difference come out to be 15.2 Kelvin, right? And the thickness of the slab is 25 millimeter, that is 0.025 meter. So thermal conductivity that we need to find out is Q upon A upon delta T upon delta X. So this comes out to be 0.0577 watt per meter Kelvin. So the answer is B. Correct. Okay. Okay. So we have 2 more questions for today. So let us proceed to the next question now. Okay. The temperature distribution across a wall 1 meter thick at a certain instant of time is given as A plus Bx plus Cx square, where T is in degrees Celsius and X is in meters. While A is equal to 900 degrees Celsius, B is minus 300 degrees Celsius per meter, and C is 50 degrees Celsius per meter square. A uniform heat generation is 1000 watt per meter cube is present in a wall of area 10 meter square. Okay, so the cross-sectional area of the wall is given. The heat generation is given as 1000 watt per meter cube. A, B, C are the constant for the equation of the temperature equation, that is all temperature distribution equation, that is already given. So the constant values are also given, that is 900 degrees Celsius for A. For B, it is minus 300 degrees Celsius per meter. And for C, it's 50 degrees Celsius per meter square. Okay. So we have to find out the temperature distribution across the wall of 1 meter thickness. That is, the thickness of the wall is 1 meter, right? And the properties, other properties is also given, as the density is given as 1600 kg per meter cube. The thermal conductivity is given as 40 watt per meter Kelvin, and the heat capacity is given as 4 kilojoule per kg Kelvin, right? So starting with the understanding that this is a case of one dimensional in space, that is spatial direction, transient heat transfer, determine the rate of change of energy storage in the wall. So We have to find out the rate of change of energy storage in the world. So if we go with the basic, we have already understood how to find out the inflow of heat, outflow of heat, what will be the heat stored, and what will, if the everything we calculated, and the heat generation also we consider into account, what will be the energy storage, change in energy storage, we can find that out. So just apply that basic, and the temperature distribution is also given, and every other values are given. So you calculate this. Okay. So I'll be waiting for you to solve this. I'll just go and come in 2 minutes, and you guys solve it. Okay. I'll just take a quick break while you keep solving this. Uh, Hi. Anyone with the solution? No one have solved this. Just start from the basic, you will be able to solve. Anyone there? Hello? Is anyone there? Okay. Have anyone solved? Have you solved, Shanchita? Is anyone having any doubt that you want to discuss about? I'm all ears. Anyone having any doubt? Or anything like how you will proceed? I can give you some small hints.
Ma'am, my doubt is whether a heat diffusion equation will be used here.
Mm, what do you think? What is being asked here?
Rate of change of energy storage in the world.
Hmm. Then will it be required?
No.
Just normal energy balance is applicable. Heat effusion equation is not required, right?
Yes, ma'am.
Hello? Yeah. You can like see the Fourier's law is been derived from all the way from that, right? So you use that. And for balancing the energy, you can use the normal energy balance. Like what is in, what is out, what is generated, and what is the storage, right? Use that and solve this and tell. Anyone? Everyone is present there or not except for Shanchita? Okay, I don't think others are present. Shanchita, have you solved it?
No, ma'am, I'm not getting the right
Uh,
answer.
See, you will just use the Fourier's law for solving the heat flux, right? And
Yes,
then
ma'am.
you just use the heat flux, balance it out with energy in, out, and everything. The main equation, like, is if there is a body, energy is entering, energy is leaving, energy is generated, and some energy is stored.
Yes,
So
ma'am.
how you will balance it? And the flux, you just replace it with Fourier's law. Understood?
Yes, ma'am.
So
Ma'am, I'm
for,
trying.
yeah, do that.
Ma'am, the conservation of by using conservation of energy,
Hmm.
uh, that equation energy entering plus energy generated minus energy out is equals to energy stored.
Correct. Correct.
Uh,
That only.
yes, ma'am. Then, ma'am, in energy in, that QX will be replaced by the heat flux by Fourier's law.
Yeah, correct.
Okay. Then
Like,
heat.
don't use the heat flux equation. You multiply it with area, so it will be heat flow, right?
Yes,
From the
ma'am.
Fourier's law.
Yes.
So area is also given here in the question.
Yes, ma'am.
So just use that. For in, what will be x? X will be 0.
Yes, ma'am.
And for out, there will be certain value of x, that is L. That is the thickness of the slab or wall.
Ma'am, but that is not good. Yes, ma'am. Given.
No, it's given at the first of the question itself.
Okay.
But you first differentiate the temperature with x. Whether x is required or not, just check it out.
Yes, ma'am.
And if x is required, then at x is equal to 0, there is one value, and at x is equal to L, that will be the outlet. That is the Q out, right? Energy out. So
Yes,
just
ma'am.
replace that in the main equation. And generation is also given. So use that to find out the energy stored.
Ma'am, that E out will be how much? Like,
Just replace x with L. See, there is a equation for temperature is given, right? And in Fourier's law, it is dt dx. So you
yes,
will
ma'am.
differentiate it with x. So there will be one value. So there is x. So x, what is inlet? Inlet of the wall, there will be x will be 0, right? And at the
Yes, ma'am.
outlet, there will be x will be L, because
Yes,
it will
ma'am.
be traversed x like L distance, right? Because the
Yes,
thickness
ma'am.
is L. So it will be x equal to L. So just replace that, and generation is also given. So just replace all of them in the main equation that you already said at first.
Yes, ma'am. And still the answer is not matching.
What have you done? Tell me.
First, in E in, I have applied that Fourier's law K A into T by dx,
Hmm.
and there I have differentiated the t as function of x, so it
Hmm.
comes out to be b plus cx square.
Hmm. B
And
plus C x square, how? You will differentiate it, no?
yes, ma'am, yes, ma'am.
C
And
x square, you will
two
differentiate it.
cx,
Yeah, correct.
yes,
Now
b
do
plus
that.
two cx, and then
Hmm.
there
Now,
x equals to 0, so cx term will be cancelled.
hmm. It is for inlet.
Uh,
For outlet,
yes, ma'am.
you
And
put
ma'am,
everything now, you will get the answer.
yes, ma'am. Okay, I'm trying once again.
Ah, sure. Have you solved it?
Yes, ma'am.
Okay, tell me the answer.
I'm not sure.
Which Which one came?
Well, it is coming to be 79,000.
Huh?
But it is not that 79, I don't know.
Like where have you, where you are thinking you are at fault?
Ma'am, in during E in, I did that x equals to 0. Then
Hmm.
in E out, I substituted like first differentiated.
Hmm.
Uh,
No, differentiate once only. In both the
yes, ma'am,
equation,
yes,
it will
ma'am.
be same. Just replace x with 1 0 and another portion it will be L.
Yes, ma'am.
L value is already given.
Yes, ma'am. Yes, I got something there. One minute. No, it's not coming.
Okay, no problem. You try that later.
Yes,
But this is the way.
ma'am. Yes,
We'll check out the solution once.
yes, ma'am.
I'll upload the recording later and you can check and you try the solution by yourself.
Yes, ma'am.
Okay. This is the question's answer. So first, as I've already said, we will apply Fourier's law and we will differentiate the temperature distribution equation that is already given there. So it will come as B plus 2Cx, right? So for the inlet axis 0 at that position. So
Yes,
sorry.
ma'am.
So yeah. So we will find out Q in to be 120 kilowatt. Okay.
Yes, ma'am, I got that.
Okay, then out will be the out will be what will happen. Just another thing that will add up here is 2cx. C is already given as 50 degrees Celsius per meter square, and x will be 1. Then I've already said the thickness.
Yes,
So it will come out to be 160 kilowatt. Have you got
ma'am.
that?
That makes no, ma'am. I got 80 kilowatt.
No, it
I,
will be 160. You have missed one 2, I guess.
yes, ma'am. That's why it's coming
Hmm.
out.
Okay. So, so now we already know that energy in plus energy generated minus energy out is equal to energy that is stored, right?
Yes.
So,
Mm.
energy generated is the heat flux that is generated. The heat flux that is generated is already given here. What is given? It's given
1,000.
as,
Yes.
where it's given? Yeah, it's already given as 1000, right? But
Yes.
it's per unit volume. Just like keep that in mind. So we have to
Yes.
multiply that with volume. So the surface area is already given as 10 meter square. The surface area with perpendicular to which the flux, the heat flux is coming. So that is 10 meter square and 10 meter square into 1. So here we can see they have done like that only. So 1000 into 10 meter square into 1 and 120 kilowatt plus that minus 160 kilowatt. So it will come out to be minus 30 kilowatt. That is
Okay.
answer will be C. Okay.
Yes, ma'am.
So let us proceed to the next question. This question number 13 is linked to the question number 12. So it is a extended portion of question number 12. So what we need to find out here? So determine, this is the last question. After that we will turn off today's class. So determine the time rate of temperature change at x is equal to 0.25 meter. So total thickness is 1 meter and here at x is equal to 0.25 we have to find out the time rate of temperature change, that is LT del T, small t, right, in the system described in question number 12. That is in this question. In this question, what will be the
Ma'am,
time
actually,
rate of,
I'm
yeah,
not seeing the question slide.
okay. I think the answer slide is shared. Wait. It's visible now, right? Yeah. So we just have to find out the time rate of temperature change. So that is, we have to find out del T del T. So here, what we need to apply to find out that? You think about that, like where del T del small t is found. So we just have to apply that equation, and
Heat
directly we
equal
can find, yeah,
channels.
and directly we have to, like, we can find out del T del T, right? So we have to
Okay.
find out at x is equal to 0.25. That is not at x is equal to 1, x is equal to 0.25.
Yes,
Okay.
ma'am.
So this is very easy question. So I'll give you 2 minutes to solve this, and then we'll turn off today's class.
Yes, ma'am.
Okay. I'll keep this page open so that you have you have all the values here. And we have to find out at dt at x is equal to 0.25 meter. Okay.
Ma'am, can you show the options?
Yeah, sure.
Ma'am, is the answer option B?
Option B. Okay. Mm, no. Check once you have missed something or not. You are pretty close.
Ma'am, I have applied the heat diffusion equation here,
Hmm.
and then then we have to differentiate it twice,
Hmm.
so the x term is getting cancelled.
Okay. Hmm.
Ma'am, and then I'm not able to figure out what will be done.
You are right only. Just you have missed something.
Yes, ma'am, I'm checking again.
Something you have missed. Just check that out. It will be independent of position as it is a double derivative.
Ma'am, option C.
Hmm. Yes. Have you got the where the minus sign left out?
Yes, ma'am. Yes, ma'am.
Okay, sure. So let me share the solution now. Okay. Solution slide is visible, right?
Yes, ma'am.
Mhm. So, first, as I've already said, that we will take the heat conduction equation. Here, first of all, like what we need to find out the del T del T, right? That is the temporal change of the temperature. So, first we need to find out del square T del X square. So, if we will double derivative it, as you have already found out, it will be minus 100 degrees Celsius per meter square.
Yes, ma'am. Yes, ma'am.
Yeah. And so we will just put every values here as it is independent of position, as it's already said here. So we will put every value, that is, what are the values here? First we will put the value of K, thermal conductivity. So it is 40 watt per meter Kelvin, and
Yes, ma'am.
then the density, it is 1600, and then thermal heat capacity, and that is 4 kilojoule per kg Kelvin, and then the del square to del X square, that is already came out to be minus 100 degrees Celsius per meter square. And then
Yes,
the
ma'am.
Q dot, that is the heat generated, that is the heat flux here, it is Q dot, small q. So heat flux is already given as 1000 watt per meter cube, and upon rho Cp, rho is already given as 1600 and Cp is
1600.
given as 4. Yeah, so we will just solve it out, so we will get us minus 4.69, that is option C. Okay.
Yes, ma'am.
Okay, then this is it for today. So we'll end the class. Thank you for joining. I'll meet you in the same time, that is 7 p.m. next week. Okay. Bye bye.
Thank you, ma'am.
Welcome.